Okay, so let me start from where we stopped last time, but then we will do a little bit of recap. So we start with a continuous parameter stochastic process such that 1 dash, 2 dash and 3 dash hold. So 1 dash being the independent increments property, 2 dash being the stationary and Poissonian increments property, and 3 dash being the process starting at 0. Now we define for every non-negative integer n, Sn dash to be the first time when the process n dash t, first time t when the process n dash t touches or exceeds n. This will be our init arrival time, so to speak. And then we find the successive differences to compute the inter-arrival times, quote unquote, xi dash, okay, which is si dash minus si dash, si1, si, s dash I minus 1. Okay, so xi dash is the successive difference between si dash and si minus 1 dash. Okay, for every positive integer I. Now clearly, we have told this last time also, since all the nt dashes are non-negative, it's clear that s dash 0 is 0 with probability 1. On the other hand, because of the way we defined xi dashes, Sn dash is just the sum of x1 dash, x2 dash up to xn dash for every positive integer n. Now it's easy to check the way we have defined things is that n dash t counts quote unquote the number of arrivals up to time t, which means n dash t is the maximum n bigger than or equal to 0 such that Sn dash is less than or equal to t. This is true for every t non-negative, every real number t non-negative. And this is obviously tailor-made because the way we have defined things. Therefore, it will be established that n dash t is a homogeneous Poisson process with rate alpha the moment we verify that the sequence of x dashes, namely x dash 1, x dash 2, etc., it's an IID, it's a sequence of IID random variables following exponential alpha distribution, exponential distribution with parameter alpha. This is what we call the equation hash. And of course, once this is done, this proves theorem star star, okay, which says that if n dash t is a process satisfying 1 dash, 2 dash, and 3 dash, then it has to be a homogeneous Poisson process with rate alpha. So therefore, we are in this setup where n dash t is a stochastic process satisfying 1 dash, 2 dash, and 3 dash, and we define the so-called arrival times, Sn dash, and the so-called inter-arrival times, xi dash, as before. Now, in order to show that a sequence of random variables are IID following exponential alpha, by definition, this is same as showing for all positive integer k bigger than or equal to 2, the random variables x1 dash, x2 dash up to xk dash are IID exponential alpha. So this is what we are going to do. At least we are going to sketch how to do this. Okay, we won't actually not sketch the general case. We'll only sketch the proof in the k equal to 2 case. So in other words, we'll sketch how to show x1 dash and x2 dash are IID exponential alpha. The general case is just more notations, that's all. Idea is the same, and it will be left as an exercise for you. I'll actually give 2 exercises, combining which you will get the result in the general case. As a warm-up question, we asked last time, what is the distribution of x1 dash? And x1 dash happens to be equal to s1 dash because s0 dash is 0, okay, with probability 1. We answered this as well. And quick recap of how we answered it. The range of S1 dash was 0 infinity, that's clear because S0 dash is 0. So therefore, the first time this becomes 1 or more has to be something positive. Now take any u positive, then the probability that S1 dash exceeds u means up to time u, definitely you have, okay, so instead of putting it this way, probability of S1 dash exceeds u is same as saying infimum of t bigger than equal to 0, nt dash bigger than equal to 1 exceeds u. So the first time nt dash becomes 1 or more is definitely after u, which means at the point u, the n dash process is definitely not 1 yet or more. So therefore it has to be 0 because it starts at 0. It cannot become 1 or more, so it has to be 0. Okay, so these two are same events, so therefore they have the same probabilities. And also n dash u being a Poisson with parameter alpha u, which comes from the properties 2 dash and 3 dash combined, we get that this is e power minus alpha u. Okay. So this shows, so once you find the survival function, you also find the distribution. This shows that x1 dash, which is equal to s1 dash, they follow exponential alpha. They're the same random variables and they follow the exponential distribution with parameter alpha. Now our plan, okay, we'll just prove, as I said, we'll sketch the proof rather, x1 dash and x2 dash IID exponential alpha. And the plan is to find the joint distribution of s1 dash and s2 dash, and then compute the joint distribution of x1 dash x2 dash from there, which is a linear function of s1 dash and s2 dash as we saw last time. So one thing that we observed last time is that this set of all t bigger than or equal to 0 such that n dash t bigger than or equal to 2 is already contained in set of all such t such that n dash t is bigger than or equal to 1. That's because if n dash t is bigger than or equal to 2, it's already bigger than or equal to 1. And we know that a bigger set should have smaller infimum. So therefore, infimum of this should be smaller than or equal to infimum of this smaller set. That says S1 dash is less than or equal to S2 dash. Therefore, the joint range of S1 dash and S2 dash, S1 dash is positive, we already know, because it's an exponential random variable. So is the set of all possible small s1 comma small s2 such that s1 is positive and s1 is less than or equal to s2. Therefore, now the first step of finding the joint distribution of s1 dash and s2 dash would be take a rectangle inside this set. So basically take numbers u1, t1, u2, t2 such that u1 is positive. All of them are positive actually. u1 is positive is enough for saying that because everything else will be bigger than u1. u1 is less than t1. t1 is in turn less than or equal to u2. And u2 is strictly less than t2. Okay? And all of them are positive. Find such numbers and then compute the following probability. So this would be our first step. We'll compute the joint probability of S1 dash being between U1 and T1 and S2 dash being between U2 and T2. Here we take the strict inequality on the left side for both and weak inequality on the right side for both. So we want to find this probability. So that's our first step. So let's try to compute this thing. Now note that S1 dash is nothing but the infimum of this set. On the other hand, S2 dash is the infimum of this set. Now the point is, somehow we have to convert everything in terms of this n dash process. Why? Because S1 dash and S2 dash are reasonably complicated looking functions of that process. On the other hand, the distributions of Sn dash are completely specified in the sense that we know that n dash t process satisfies stationary and independent increments and also the increments of Poisson. So we have to encache that. So everything has to be written in terms of this n dash t process. Okay, that's the idea. So here it's written, but it's written in a very complicated way. But we will try to analyze the situation and see whether this can be written something more, simpler format. Now, what's that? So that would be, if you see the infimum of this is strictly bigger than U1, and we have already used this in the calculation of distribution of S1 dash. This is strictly bigger than U1 means up to time U1, there is no call. So in this interval, there is no call. On the other hand, the first time it touches or exceeds 1 has to be less than or equal to T1, which means at least one call has to come in this interval. However, I say that it has to be exactly one call because of the next thing. The next statement says, first time it touches or exceeds 2 is after U2, which means up to T1 definitely there has to be exactly one call. It cannot be more than one call. Of course, it has to be at least one call so that this inequality is honored. But in order to honor this inequality here, that the second n-t becomes 2 or more strictly after time U2, definitely there cannot be any more call other than one call. So it has to be exactly one call. On the other hand, for the same reason, we cannot have any call in this interval because the first time it becomes 2 or more is after U2. So therefore, in this interval, there cannot be any call at all. On the other hand, we have to honor this inequality here. This has been already honored. So this, in order to honor this, you need that at least one call has to happen in this interval. Note that it can be more than one also. There is no restriction other than this. So therefore, it has to be at least one call in this interval. Okay? And if this happens, this will also happen. So therefore, what we get from here is that the n dash of U1 has to be 0. N dash of T1 minus n dash of U1, which is the number of phone calls in this interval, has to be 1. N dash of U2 minus n dash of T1 has to be 0, which is the number of phone calls in this interval. Note that this interval T1 and U2 can be 0 and they can be equal. So this can be 0 anyway, but that's okay. That's a part of the assumptions. On the other hand, n dash T2 minus n dash U2, which is the number of phone calls here, has to be bigger than or equal to 1. Okay? So we have been able to completely unfold this notation and write everything in terms of the original n dash T process. Okay? Now let's use the fact that the n dash process has independent increments. So number of phone calls here, number of phone calls here, the number of phone calls here, and the number of phone calls here are all independent. If we do that, then we are going to get that this is going to be the product of these marginal probabilities. Okay, this is where we are using the assumption 1 dash.